Hello everyone. Today we have to start with this new topic about profit margin and how we can actually calculate the profit margin for any chemical process. So let us see what is an equation that we have here. Profit margin, it is equal to value of the products minus cost of the raw materials. So it is quite simple. If the profit margin it is greater than 1, then the process is reliable, and if the value for the profit margin it is less than 0, then the process is not reliable and we have to see an alternate route. For example, we are supposed to produce the benzene from toluene, so there could be two alternative routes that we can follow. So the first route is the toluene hydrodealkylation process, where toluene reacts with the hydrogen to produce benzene and methane. And the second route we have here is the toluene disproportionation reaction, in which we use the two molecules of toluene that can be decomposed into the benzene and xylene. Now, in between these two routes, we will see that which route is more reliable and more economical, and it can generate more profit. So let us see what how we can calculate that profit. So some processes are more sensitive to product and feed prices than others. So when we make different processes, or when we design different processes, some of the processes they are more sensitive to the feed and the product prices. So that is an important criteria that we need to see when we try to calculate the profit margin. Average cost data over a period of several years should be used in evaluating the profit margins. Now, when you are specifying the cost of the product or cost of the raw materials, so they are subjected to the market fluctuation. So we have to use the data from the past years to get the average data that could be more reliable to estimate the price of the raw materials and the products. Cost of raw materials play a role in deciding which chemical path to choose to produce a given product. So depending on the price of the raw materials, we can decide that which route is more reliable and it can generate more profit. So let us see how we can calculate the profit margins of the hydrodealkylation process. Now here from tables 8.3. Now this table 8.3, it is from your book. It is given on page 212, and it discusses, or it gives you the information about the price of the utilities, maybe the pressurized air, steam, electricity, or any fuel. Okay, so you can follow this table and get the prices of the utilities. Table 8.4, it will give you the information about the price of the chemicals. So using these two tables, we will try to see what is the profit margin of the hydrodealkylation process. Okay, from table 8.3 and 8.4, we get the following prices of the raw materials and the products. So the benzene price that we get from table 8.4, it is 0.919 dollars per kg, and toluene price is $1.033 per kg. From table 8.3, we can get the price of the natural gas, that is $11.10 per gigajoule, and we can convert this one into the dollars per standard cubic feet, and finally we can have the value of the natural gas in dollars per kg, which is $0.302 per kg. Similarly, the price of hydrogen, we can find that it is $1 per kg. Now we have to select the basis of the reaction. So using 1 kmol of toluene as a feed basis, what we can do here. So you have to keep the reaction of the toluene and the hydrogen in your mind when you are doing this profit margin analysis. So 1 kg, 1 kmol of toluene feed basis, we can have this information. So if I take you back to the reaction, what we have here. Now this reaction, if you calculate 1 kmol of the toluene, so you can study what is the weight of this toluene, what is the weight of this hydrogen, then what is the weight of this benzene and methane. We can actually calculate what is the profit margin. So let us see this one. So 1 kmol basis of the toluene, it will contain 92 kgs of toluene. So 1 kg of toluene, it is equal to this one, and 92 kgs of toluene will cost you $95.04. Similarly, 2 kg of hydrogen, it will be equal to $2. And now we have to calculate the value of the products that we can generate from the given pathway. So we can have 78 kgs of benzene, and similarly you can multiply the cost of benzene with the number of kgs. So you can have the value for 78 kg of benzene, that is equal to $71.68. Similarly, you can calculate the value for the methane for 16 kgs, that comes out to be $4.83. Now, how you can calculate the profit margin? The value of the products minus value of the raw material. So you can have the value of the products minus value of the raw material. So that will give you minus $20.53. So minus sign shows you that this process is not reliable. And if you divide this minus 20.53 with the 92 kg of toluene, then you can have the value in terms of loss for producing 1 kg of toluene, that is 0.223 kg, $0.223 per kg of toluene. So from here we can see that this process is not reliable and we have to see some alternate route. Then clear? Based on this result, further investigation of this process is definitely not warranted. So we will not follow this pathway, and we will see some other pathway to produce the benzene. Despite the results illustrated in the earlier example, benzene has been produced for the last 50 years and is a viable raw material for the host of petrochemical products. How is this possible? Benzene can be produced via at least one other route that is less sensitive to changes in the prices of toluene, benzene, and natural gas. Now we can have another route and through which we can produce the benzene, and it is less sensitive to the market changes or in the prices of toluene, benzene, and the natural gas. One such commercial process is the disproportionation or transalkylation of toluene to benzene and a mixture of para-orthomethazylene by the following reaction. Now here we will take the two molecules of the toluene, that will give you one molecule of benzene, and we can have some xylenes. Okay, so we will see that how we can calculate the profit margin from this equation. So we can get the price of this toluene. Similarly, we can have the price for this benzene, and we can also have the price for this xylene. So what we can do here again, evaluate the profit margin for the toluene disproportionation process. So on table 8.4, we can have the value for the mixed xylenes. Okay, so this one here represent you the mixed xylenes. Now, if you go to the table 8.4, you will see that the mixed xylenes, you can have the price $0.82 per kg using 2 kmols of toluene feeds at the basis. The cost of the raw materials, it will be 184 kg of toluene, and it will cost you $190.07. Similarly, you can calculate the value of the products. So 78 kg of benzene will cost you 71.68, and 106 kg of xylenes or the mixed xylenes, it will cost you 86.92. Now once you have this cost information for the raw materials and the products, you can actually calculate the profit margin. So we can put this one into the main equation. So the cost of the raw materials minus cost of the product, it will give you this equation. Now we can get the value dollars in dollars, $31.47, or in terms of dollars per kg of toluene feed, we can have 0.171 per kg of toluene. Now this number, although it is showing you the negative sign and it shows that this process is also not profitable, but this process is more reliable than the HTA process, because the profit margin or the loss that we can see here, it is less compared to the loss that we can see in the HTA process. Now how we can actually make this process more profitable? So let's see that one. Based on the results of example 2.2, the production of benzene via the disproportionation of toluene is better than the toluene HTA process, but is still unprofitable. However, a closer look at the cost of purified xylenes from table 8.4 shows that these purified xylenes are considerably more valuable than the mixed xylene. Now what we can see here, that the cost of the mixed xylene, it is very less, it is $0.82 per kg, but if somehow we can convert that mixed xylene into some purified xylene in terms of metaxylene or some orthoxylene, then the value for this product is much higher than the mixed xylene. So this is the thing that we will see here. Now here we can see that the mixed xylene it will cost you $0.8200 per kg. However, if we can convert that mixed xylene into orthoxylene or some metaxylene, then the cost of this one it is very much higher than the mixed xylene. So we will see that how we can change the process flow to make the highly purified xylene instead of this mixed xylene that could lead the process towards more profitability. So, therefore, the addition of a xylene purification section to the disproportionation process might well yield a potentially profitable process that is worth further more detailed analysis. Okay, so if we can convert this xylene into metaxylene or orthoxylene or some purified xylene, we can actually make this process more profitable. Okay. Now let us see what is the step number three in developing the conceptual process diagram. It is the recycle structure of the process. This step basically involves the recovery of materials and energy from the process. It may be instructive to break down the operating cost for the typical chemical process. So whenever you are trying to evaluate the process performance, then we need to consider what is the recovery of material and how much energy is being utilized to produce those products, and we have to incorporate those energies in the fuel cost, and then we will see that process is either profitable or not. Peter and Timmerhorst suggest that raw materials make up between 10% and 50% of the total operating cost for processing plants. However, due to increasing conservation and waste minimization techniques, the estimate may be low, and an upper limit of 75% is more realistic. Okay, so earlier what we have seen that the raw material cost it will include, or it will have like a 10 to 50% share in the operating cost of the processing plant, but due to the better techniques in the conservation of energy and the mass, and we have used some recycle structures and waste has been minimized. So now 75% of the total operating cost it will include the cost of the raw materials. Because these raw materials are so valuable, it is imperative that we be able to separate and recycle unused reactants. So the cost of the raw material it is basically very important in determining the process profitability and reliability. So we do not want to waste any of the unreacted raw material. So we have to see what could be the recycle structure of the process to we can maximum utilize the reactants. The extent of recycling of unused reactants depend largely on the ease with which these unreacted raw materials can be separated from the products that are formed within the reactor. Now, when you are trying to reuse the unreacted raw material, then we have to consider the recycle structure, and because the separation of the reacted raw material and the unreacted raw material it depends on the separation techniques that we have to use in the process. So we have to also consider the equipment cost for the separation and what could be the utilities that are being used for the separation. So all of these factors will influence the recycle structure of the process. Now let us see how we can actually calculate the efficiency of the reactor in the single pass conversion, overall conversion, and the yield. So what is a single pass conversion? A reactant consumed in the reaction divided by reactant feed to the reactor. So this one is a single pass conversion. You must have studied this one in CHE201 and 202. So single pass conversion it only gives you the conversion around the reactor. Okay, it will not consider any of the recycle stream. However, in the overall conversion, the reactant consumed in the process, reactant feed to the process. So here in the overall conversion, we have to also consider the recycle structure and how much is the reactant consumed overall in the process and how much is the reactant fed into the process. The yield, we have studied this one earlier, moles of the desired product, moles of limiting, reactant reacted. Okay, so the yield of the any of the reaction it is given by the desired product divided by moles of limiting reactant. So let's see how we can calculate the single pass overall and the yield of the hydrodealkylation process. So benzene process for the most costly reactant toluene. So we will consider the toluene and we will see that how much of this toluene is getting converted into the benzene. Okay, so in the single pass conversion, now to get these values, you have to go back to the stream information of the HTA process, which is given on the page 14 of your book. So let's see this one. On page 14, you will see this table here, which is actually connected with the HTA process flow diagram on the same book. Okay, so maybe you can hear this one is process flow diagram, and the stream numbers are here, and according to these stream numbers you can see the uh, information for the mass flow rates here in the table 1.5. Now from here table 1.5 you will get the values for the toluene flow rate in the inlet, in the outlet, around the reactor, and the overall conversion, and then we will see what is the single pass conversion, overall conversion, and the yield. Okay, so in the single pass conversion 144 stream, 144 k moles per hour, which is the toluene flow rate inlet to the reactor, and then 36 it is the moles of the toluene that is coming out of the reactor, and then the total moles of toluene that is going into the reactor. So we can solve this one and it comes out to be 75 or 75%. In the overall conversion, we will see that 108.7, the amount of toluene that is fed into the process, and then we will see that minus zero point 0.4, this is the amount of the toluene that is going with the benzene in the stream number 15, and then we can have 4.31, it is the amount of toluene that is going into the vent uh, as a waste stream. Okay, so this is the conversion here, and the total toluene that we fed into the system, it comes, the overall conversion comes out to be 99.3%. Similarly, you can calculate the yield of the toluene. Now here, what is the desired product, which is the benzene here in the stream number 15. Okay, so benzene in stream number 15 plus benzene in the stream number 16, which is going into the vent. So this is the total production of the benzene, and divided by the toluene that we fed into the system minus toluene that is going with the benzene, and then how much of the toluene is wasted into the fuel gas. So in this one the yield comes out to be 99.95%. Now these are the three indicators that we usually use when we determine the amount of conversion of the reactant into the product, and how we can actually optimize the overall conversion and the yield of the process. Now here this is a flow sheet again, so you can see different stream numbers, and here is the table again, so that you can use this table to analyze the single pass conversion, overall conversion, and the yield of the reaction. Now let us see what is a single pass conversion. Single pass conversion tells us how much of the reactant enters the reactor is reactor. Okay, so single pass conversion, it gives you how much of the reactant is reacted into the reactor. The lower the single pass conversion, the greater amount of the recycle. If the single pass conversion is low, then obviously we have to use a better recycle structure, and because we cannot waste any raw material or the feed, so we have to optimize the recycle structure of the process. Single pass conversion affects equipment size and utility flows. Obviously, when we are using the single pass, if the single pass conversion is low, then we have to use a recycle structure that will increase the size of maybe the reactor or the utility flows. Okay, raw materials cost are not changed significantly by the single pass conversion. So single pass conversion, it is basically the process configuration, and it will not affect the cost of the raw material. Okay, single pass conversion of the hydrogen in HT process is kept low to reduce coking of the catalyst. Now here in the single pass conversion, you have to also keep in mind the catalyst working. Okay, so we just want to keep the catalyst bed active and reduce the coking on the catalyst. So in that particular case, we need to keep the hydrogen concentration low around the reactor. Overall conversion tells us what fraction of reactant in the feed to the process is converted into the product. So here we have to talk about the overall conversion of the feed to the product. Higher overall conversion, 99.3%, is typical for the chemical process. So higher overall conversion above 99.36% is usually required for the chemical processes. Higher overall conversion shows that unreacted raw materials are not being lost from the process. So if the overall conversion of the process or the reactant is high, then it is an indicator that we are not wasting any raw materials from the process. Low overall conversion of hydrogen in the HTA process indicates poor raw material usage. Okay, so if the hydrogen consumption is low in the overall conversion, it will show that the overall consumption of the raw material is low. The yield tells us what fraction of limiting reactant ends up in our desired product. So it is the definition of the yield. Competing or side reactions may reduce the yield. If there are some side reactions are going on or some waste streams are being produced from the process, then obviously the yield of that system will be low. Yield of the hydrodealkylation processes are generally high, 98 to 99% from these two companies. Okay, so in the hydrodealkylation process, the limit for the yield that is defined by these two companies, it is between 98 to 99%. Now let us see what is the basic recycle structure of the process. Separate and purify unreacted feed from products and then recycle. For example, tolling. Now, if we are giving, if we look at the around the reactor, then what is our aim to get the maximum conversion of toluene into the benzene. So if there is an incomplete conversion of the toluene, then we have to separate the unreacted toluene and then we have to recycle back into the process. Recycle feed and products together are used a purge stream, for example, hydrogen with purge as a fuel gas. This is the second recycle structure that we can use, in which the recycle feed and products can be used together, and you can use some purge stream. Okay, so we will see the details of this structure later. The third structure that we can use for the recycle is the recycle feed and products together, but do not use a purge stream. Now in this case, we will recycle the feeds and the products together, and there will be no purge stream. So practically we are trying to reduce the use the toluene wastage from the process, and we are maximizing the recycle rate. Okay, now for here, what you can see here, this 2 moles of the benzene, it can give you the diphenyl and the hydrogen, but if there is some production of the diphenyl in the process and we recycle back into the process, then we can actually get the benzene back. So we will see that how these structures can be used to minimize the toluene wastage from the process, and depending on the type of process that you are building for the conceptual design, which recycle structure best suits your design. So number one, separate and purify. So this is the point number one. First thing that you can do, that if you can easily separate the undesirable product from the desirable product, you can do that thing. But what things that you should keep in the mind? Ease of separation depends on. So the separation can be done that what conditions, temperature and pressure are necessary to operate the process. So to separate the undesirable product from the actual product, which separation process you are going to use, and what is the temperature and the pressure requirement. Are there differences in physical and chemical properties for the species to be separated, large or small? And then you have to consider what is the physical and the chemical properties between the products, between the actual products and the undesired products, and whether the physical separation is more easy or the chemical separation is more easy. For the separation of methane and hydrogen, first they look at the distillation. Now, if you are separating some kind of gases from the process, then the thing that we can do is the distillation process. And for the distillation, we have to maintain some cryogenic conditions. So normal boiling point of methane is minus 161, and normal boiling point of hydrogen is minus 252. And now looking at these temperatures, you can have an idea that how much energy you would need to spend to separate these two gases, and then you would see that whether it is practical to separate these gases or not, or if some of the gas it is not reacting chemically within the process, or it is not affecting the product quality, then either it can be sent into the atmosphere, or we should recycle. So there are certain conditions that you have to see from the economics point of view. Separation should be easy using distillation due to large difference in the boiling points of the two components. Now, if you go for the cryogenic distillation, you would see the temperature here, and from the distillation point of view, if you can refrigerate the overall system, and you can see that there is a high difference between the boiling points. So practically, it is possible to separate these two gases. Then you have to see what is the energy requirement in the refrigeration process. However, in order to get a liquid phase, we will have to use the combination of high pressure and the low temperature. Now, to separate these two things, methane and hydrogen, we need to create the cryogenic conditions, and we need a very high pressure and a low temperature. This will be very costly and suggests that distillation is not the best operation for this operation. Okay, so we can do the separation, but if we calculate the economics and the energy requirements, then we have seen that the cryogenic separation through distillation, it is not practical, and it will cost you more in the process. Now, what could be the other techniques? Absorption. It might be possible to absorb or scrub the methane from stream number 8 and 17 into the hydrocarbon liquid. However, suitable liquids have to be identified considering the solubility parameters for both methane and hydrogen in different liquids. Okay, now there could be another technique. If we want to remove the methane from the benzene, then the second way of removing that methane is by the absorption. So we can select certain chemicals or liquids that can actually selectively absorb the methane gas from the process. Other thing that we can see here, pressure swing adsorption. Using a pressure swing adsorption, the methane would be preferentially adsorbed on the surface of the sorbent, and the stream leaving the unit would contain a high proportion of hydrogen than the feed. This could be applied to the HTA process. Now, in the pressure swing adsorption, this mechanism is behaves in a way that the adsorption is carried out at high pressure on some sorbent, and when you reduce the pressure, the gas is then again desorbed from the sorbent. So this is how the pressure swing adsorption works, and maybe we can apply that process to the H2A process, in which we adsorb the highly pressurized hydrogen on some sorbent, and then when we reduce the pressure on that sorbent, the hydrogen is released back. Then the third separation technique, it could be the membrane separation. Hydrogen passes more readily through certain membranes than the methane. This could be applied to the HT process. Now we can also use some kind of membrane that can through which the hydrogen can pass, but the methane cannot pass. So this is how we can use the membranes also to separate some of the chemicals or some of the gases from the process that are undesired. Now here we will see the example 2.4. What process should be used in the separation of toluene and benzene? Now, if you want to separate the toluene and the benzene, which process can be used? For example, in the distillation, normal boiling point of benzene is 79.8, and normal boiling point of toluene is 110. Separation should be very easy using distillation, and neither excessive temperature nor pressures will be needed. This is a viable operation for this separation of benzene and toluene in the HT process. Now, looking at these temperatures, which are not very high, and the boiling point difference between the benzene and toluene exists, so there are no azeotropes formation also. So we can use the distillation process to separate these two chemicals.